Chapter 6, Section 6. Cramers rule. Cramers rule uses something called matrices. That's the plural of the word matrix. That's singular. What a matrix does takes a system of equations and removes the variables to allow us to calculate the determinant. A matrix looks like this. This is what we call a two by two matrix. The first number is the number of rows, and the second is the number of columns. The rows represent the equations, and the columns represent the variables. So in this example, ABCD one, we have line 1, line 2, and this is variable X, and this is variable Y. So this is equation 1, this is equation 2. Only the coefficients are used. The coefficient of X, the coefficient of Y. So let's look at our earlier example. We have X minus Y equals 5. 2X plus Y equals 1. So let's convert this into matrices. And there's the equal sign, and this is the answer. So the answers are 5 and 1. So in the first line, the X coefficient is 1, and the other one is negative 1. The second row, 2 and positive 1. So that's how we convert a system of equations into matrices. We know this is the x variable, this is the y, and this is the solution. This is equation 1 and line 2. How about this one? And you're not limited by size. This is a 2 by 2 matrix because it has 2 variables, 2 equations. This one has 3 variables, 3 equations, so it's 3 by 3. So we have the x variable coefficient, the y and the z, and the solutions. The solutions are 0, 4, and 1. The x coefficient is 4, -5, -1, -2, 5, -2, 6, 0, -7. If it's nothing there, it's a 0. So that's how we convert from systems of equations to a matrix. Now, how do we use matrices to solve a system of equations? Well, we have to use something called the determinant. So let's pretend this is our matrix. And this is our solution. Let's call it S1, S2. The determinant you notice we now use a different symbol. Remember, mathematics is a symbolic language. To represent a matrix, these are brackets. But when we calculate the determinant, which is capital D, we use, it looks like absolute value lines. The way this is calculated, it's always by diagonals. We multiply this diagonal. So we have A times D. We subtract this diagonal. That is your determinant. So far, so good. So this is of the original equation. Notice we haven't used the solutions yet. Those have to play a point. So this is the x component, and that's the y variables. To find the x value, we need the determinant of x. the determinant of x the way we find that, since this is the x column, we take the answers and put them in the x column. Leave the y values alone. So it's going to be solution y. It's the same thing. It's the diagonals. So it's d s1 minus b s2. That's your dx. To find the y value, we need the dy. So in this one, since it's the y, we leave the x values alone. So it's a and c. And put the answers in the y column. And we do the diagonals. A S2 minus C S1. And then finally, to get the X and Y values, X is equal to dx over d. Y is equal to dy over d. And that gives us our answer. Yes. So let's go back to our example we had earlier. We had x minus y equals 5, 2x plus y equals 1. The first step is converted into matrices. So it's 1, -1, 5, 2, 1, 1. We first have to find D. D is the original equation. 1 times 1 minus 2 times negative 1. 1 plus 2 is 3. So that's D. Find D sub X. Since we're looking for X, we take the answers and put them in the X column and leave the Y values alone. Five times 1, 1 times negative 1. 5 plus 1 is 6. So D of X, or D sub X is 6. Find dy. Leave the X column alone. Put the answers in the Y column. One times 1, 2 times 5. So dy is equal to negative 9. Now you got to find X and Y. X is dx over d, which is 6 over 3, which is 2. And Y is dy over d, which is negative 9 over 3, which is negative 3. So my answer is 2, negative 3. Yes, a lot of writing, but a lot of this stuff you could do in your head. Let's do another one. Four x plus 3y equals 11. Negative 5x plus 2y equals 15. The beautiful thing about this is there aren't any fractions. The only fraction comes at the very end when you're finished. First step is what? Put it into matrix. So it's 4, negative 5, 3, 2, 11, 15. First, just find D. Take the original one. So it's 4, negative 5, 3, 2. 4 times 2, 3 times negative 5. 8 plus 15. D is 23. Dx. Take the answer, put it in the X column. Leave the Y column alone. 11 times 2 minus 15 times 3. 22 minus 45. Dx equals negative 23. And then dy, leave the x alone. Put the answers in the y column. Four times 15, 11 times negative 5. $60 plus 55 is 115. That's dy. Find x and y. Dx over d, and y is dy over d. Dx is negative 23, dy is 115. So it's negative 1 and 5. So far, so good. Let's look to see how the parallel and same line would look. X minus 3y and negative 2x plus 6y. One, negative 3, negative 2 and 6, 1 and 5. Six minus 6 is 0. And we're done. Because remember, this is the denominator. We can't find x or y. Because x is dx over d. We cannot have 0 on the bottom. So there's no solution. Parallel lines. Let's look at the second one, B. 2x plus 3y equals 6. 4x plus 6y equals 12. Find D. 2, 3, 4, 6. 12 minus 12. Uh-oh. There's going to be one difference here. Let's look at dx. 6, 12, 3, 6. 6 times 6 minus 12 times 3. 36 minus 36 equals 0. So here we're going to get 0 divided by 0. Which, because everything cancels, it's always going to, but in this one, dx would have been 1, 5, negative 3, 6. So it's 6 plus 15 is 21. So we would have had 21 over 0. That's why it's undefined. This one's 0, 0, everything cancels. Even though this is undefined, is 0, 0. And you have the same thing with the y values also. So that's how you determine whether it's here, it's infinite solutions. Same line. All right. Now, the common phrase that people always use, common sentence people use is that doesn't seem much easier. It's just cleaner, I think. But the beauty of Cramer's rule is it doesn't matter how big the matrices are. X minus 3y plus 7z equals 13. X plus y plus z equals 1. X minus 2y plus 3z equals 4. If you were to use elimination and substitution, this would take you about an hour with a lot of writing. This one is just a matter of multiplying and subtracting. Let's convert it to a matrix. Thirteen, 1, and 4. So it's 1, negative 3, and 7. 1, 1, and 1. 1, negative 2, and 3. Now, because we have more than a 2 by 2 matrix, the process here is a little bit different. Yeah, I don't want to show you the other way. This to find the determinant of this one. No, that's if you're trying to find the resulting matrix. No, this is we're trying to find a determinant. So we take the same matrix without the symbols now, just put the numbers. Repeat the first 2 columns. Now, this side will multiply these diagonals. So we have 1 times 1 times 3 plus -3 times 1 times 1 plus 7 times 1 times -2. So that way you add them. These you subtract. So it's -3 times 1 times -3 minus -2 times 1 times 1 minus 1 times 1 times 7. One times 3 is 3 plus -3 plus -14 minus -9 minus -2 minus 7. Just multiply these out. Positive, negative is a negative. Negative. Positive, negative is a positive. Positive. So those cancel. -14, -7 is -21. 9 plus 2 is 11. So my D is 10. Repeat the process now for the X, Y, and Z components with the answers going to those columns. Because your answers are still going to be X is equal to dx over D. Y is going to be dy over D. And Z is going to be dz over D. If you had a 4x4 matrix, you would take the first 3 columns and copy them. If you have a 7x7, take the first 6 and copy them over. So it's always one less than what you have. Since it's 3, I want 2. If it's 5, I'll take 4. And it'd be the same thing, diagonals and diagonals. So let's look at what 6 would, or X would be. Let's look at dx. So the answer would go in the X column. The Y would be the same. And the Z would be the same. 7, 1, and 3. So I'll take the first column and the second column and repeat them after the third column. So I'll take these 2 columns and copy them at the back. So that 13 times 3 is 39. Plus -12 plus -14 minus -9 minus -26 minus 28. So, I mean, this is the easy stuff you can put in your head. 7 times 1 times 4 is 28. 13 times 2 is 26. It's a negative. 3 times 3 is 9, negative. 39 minus 12 minus 14 plus 9 plus 26 minus 28. -12, -14 is -26. So that and the +26 cancel. -39 -28 is 11. 11 plus 9 is 20. So x is dx over d, 20 over -10, which is -2. Do the same with y and z. Any questions? Oh, you want me to do those? You sure? Well, let's go ahead and do it. Only two more rows or two more formulas. Well, if you have a 5 by 5, it's one less than that. So we take the first 4 columns and copy them over. If it's 7 times 7 by 7, take the first 6 over. Always leave the last one alone. So this one here is 3 columns. I take the first 2. If it was 4 columns, I take the first 3. So dy, leave the x alone. Put the answers in the y. So I get 1, 1, 1. 13, 1, and 4. 7, 1, and 3. Copy the first 2 over. And diagonals. Those, and those. Minus these, and these. Three times 1 is 3. Plus 13. Plus 28. Minus 39. Minus 4. Minus 7. So all the positives be 30, 41, 44, minus 50, be 43. It's -6. So y is dy over d, -6 over -10, 3 over 5. See, this method is a lot faster than the other methods. And then dz would be, leave the d alone, leave the y alone, the x and y alone, and put the answer in place of the z. One, 3, 1, -2, 13, 1, and 4. Repeat the first 2 columns. and diagonals. Hardest part about this is make sure you make them perfect rows and columns. Because if you mess up your diagonals, it's going to mess up the whole answer. So 4 times 1 is 4, plus -3 times 1 is -3, plus negative 13 times -2 is -26, minus a -12, minus a -2, minus 13. So dz would be 4 minus 3 minus 26 plus 12 plus 2 minus 13. So that's, well, 4 minus 29 plus 14. 4 and 14 is 18. Negative 42. dz is negative 24. So z would be dz over d, negative 24 over negative 10, cancels negatives. 2 goes in both of them, 12 over 5. So the place where all three of these meet would be at -2, 3 over 5, 12 over 5. That's the point where all these lines intersect in 3-dimensional space. So yeah, Cramer's rule is a lot faster, a lot cleaner, a lot easier to use than substitution, elimination, or graphing. That's the end of the class. Yay!